Hey everyone, and welcome back to Merit Mantra. All right, gear up because we're about to launch into an awesome mission deep into the world of physics. Today, our mission, should you choose to accept it, is to decode the language of motion itself. I mean, seriously, think about it for a second. What does a rocket blasting off, a Formula One car tearing up the track, and a cricket ball getting smashed for a six really have in common? Well, the answer is they all change their velocity. And that secret ingredient, that force of change, is exactly what we're here to master: acceleration. So here's our mission briefing for today. We'll start by decoding acceleration, then we'll get our hands on the source code, the kinematic equations. After that, we'll run a case study, a trajectory test, jump into some real-world physics simulations, and even tackle a special ops mission on relative velocity. And of course, we'll wrap it all up with a final debrief. Okay, team, let's get this mission started. First stop, decoding acceleration. This is the stuff that really changes the game.
So what is acceleration, really? Well, to put it simply, whenever an object's velocity changes over time, that's acceleration. It's the very heart of speeding up, slowing down, or even just changing direction.
And these motion graphs, they tell the whole story. See that first one where the velocity is increasing? That's positive acceleration. You're speeding up. The middle one, where velocity is dropping, that's negative acceleration or deceleration. You're slowing down. And that last one, a flat line, that means constant velocity, so zero acceleration. Simple as that. Okay, pop quiz time. Think about this. If a car is slowing down, is its acceleration positive or negative? Take a second. Really picture it. The answer? Well, if the car is moving forward, that's positive velocity, but it's slowing down, then the acceleration has to be negative. It's working against the direction of motion. And knowing that is the key to our next section, the source code. These are the kinematic equations, your toolkit for predicting the future of motion. Okay, so before I just throw a bunch of formulas at you, let's see where they actually come from. It's pretty cool. The total distance an object travels, its displacement, is simply the area under its velocity time graph. See how this area is made of a rectangle and a triangle? The area of that rectangle is just initial velocity times time. The area of the triangle is 1/2 times time times the change in velocity. You add those two pieces together, and you get this powerful equation for displacement. And that derivation leads us right here to your complete toolkit. These are the 3 core kinematic equations for motion with constant acceleration. You need to know these inside and out. They connect displacement, time, initial velocity, final velocity, and acceleration. Master these, and you can predict the future of anything moving in a straight line.
All right, you've got the tools. Now it's time to get our hands dirty and apply them. Welcome to our case study, the trajectory test. Let's apply this source code to a real-world problem.
Okay, here's the mission. We have an object, let's say a ball, thrown straight up at 20 meters per second from the top of a 25-meter tall building. Our job is to figure out 2 things. 1, how high does it go, its maximum height, and 2, how long is it in the air before it hits the ground, the total time of flight. Now, before we start plugging in numbers, here's a crucial question that will make solving this way easier. At the absolute peak of its flight, its maximum height, what is the instantaneous velocity of the ball? Think about it. So let's break this down using that key insight. First, to get the max height, we use our third kinematic equation, the one without time. We set the final velocity to 0, plug in our initial velocity and acceleration due to gravity, and solve. Boom! The rise distance is 20 meters. Add that to the building's height, and you get a total max height of 45 meters. Now for the time. We use this second equation, setting the final position to the ground, which is 0. It's a quadratic equation, but once you solve it, you find the total time of flight is 5 seconds. See? Mission complete. Awesome. Now that you've seen the equations in action, let's run a rapid-fire simulation. We're going from Galileo's famous experiments all the way to the driver's seat. First up, free fall. This is the classic example. If we ignore air resistance, which we often do in these problems, the acceleration is constant. It's always negative 9.8 meters per second squared, pulling straight down. This means the velocity increases in a straight line, and the distance traveled, well, that increases quadratically, giving us that perfect parabolic curve you see here. And you know who was obsessed with this stuff? Galileo. He discovered something amazing, a beautiful hidden pattern in how things fall. He found that the distance an object falls in equal chunks of time, like 1 second, then the next second, then the third, follows a simple ratio of odd numbers. 1:3:5:7, and so on. Just a really elegant piece of physics right there. Okay, let's bring this back to something we can all relate to. Driving. Here's a question for you. If you double your speed, say from 11 meters per second to 22, what happens to the distance it takes you to stop? Does it double? Triple? What do you think? Well, if you thought it doubles, you're not alone, but it's a common mistake. The relationship isn't linear at all. Stopping distance is actually proportional to the square of your initial speed. So if you double your speed, you don't double the stopping distance, you quadruple it, 4 times longer. And that stopping distance has 2 parts: the distance you travel while you're reacting and the distance you travel while you're braking. You can actually measure your own reaction time, your biological latency, with this super simple ruler drop experiment. Just have a friend drop a ruler between your fingers and see how far it falls before you catch it. You can use our kinematic equations to figure out your reaction time from that distance. It's usually around 0.2 seconds. Give it a try at home. Okay, you're doing great. Time to kick it up a notch? Welcome to Special Ops, where we're going to tackle relative velocity. This is where things get really interesting because we start looking at motion from different points of view. Let's set the scene. We've got an incoming high-speed chase. It's time to put on our action movie analyst hats. So here's the setup. A police van chasing a thief's car. The police fire a bullet. We want to know the speed of the bullet relative to the thief's car. The key is to calculate the bullet's speed relative to the ground first. Since it's fired from a moving van, you add their velocities together. Then you find its speed relative to the target by subtracting the thief's speed. And the result? A whopping 105 meters per second. That's how fast the gap is closing between the bullet and the target. Whew, we have covered a ton of ground. So let's run a final debrief to lock in all this new intel. These are your quick glance revision notes. Okay, here it is, the absolute must-know stuff from today's mission. First, acceleration is the rate of change of velocity. Simple. Second, those 3 core kinematic equations are your best friends for solving problems with constant acceleration. Third, remember, free fall is just a special case of uniform acceleration. And finally, don't forget that displacement is just the area under a velocity time graph. You know, these are the concepts you absolutely have to burn into your memory. They're the foundation for pretty much everything else you're going to learn in mechanics. It all comes back to this idea. Motion is just change over time. And physics really is the language we use to describe and predict that change. And with that, mission accomplished. You did an awesome job today. Now, if you found this briefing useful and you want more missions like this, you know what to do. Smash that like button, share this with your friends and classmates, drop any questions you have in the comments below, and most importantly, subscribe to Merit Mantra so you don't miss the next briefing. All right, that's a wrap on today's explainer. Thanks so much for joining the mission. Until next time, stay curious and keep questioning everything.